I have the very distinct pleasure of introducing Luis Chacon today. Chacon. Luis is a fellow of the American Physical Society, and he's a senior scientist in the Applied Mathematics and Plasma Physics group in the theoretical division at Los Alamos National Laboratory. Luis got his master's degree in industrial engineering, interestingly, from the Polytechnic University of Madrid, and his master and PhD degrees in nuclear engineering from University of Illinois Urbana-Champaign. After he graduated, he joined actually the theoretical division at Los Alamos as a director's funded postdoctoral fellow and became a staff member there. And around the time I met him, he was actually, he had joined the fusion energy division at Oak Ridge and then returned to live in Los Alamos in 2012. And he's currently associate and executive director of the Journal of Computational Physics. So Luis's research spans many aspects of plasma simulation and in particular algorithm development, including transport, magnetohydrodynamics, kinetic modeling in both Eulerian and Lagrangian systems. So I've worked with Luis on a number of panels, determine the future of integrated simulation in the United States, which is always a pleasure. So with following that, I'll go ahead and start, Luis.
Thank you for the nice introduction, Paul, and thank you and Christina for the opportunity to present in this venue. It's always good to reflect back on what's happened in the last few years. And this work actually spans a significant amount of time, some of it going back to 2010. So hopefully you'll find it enjoyable. I'll start slow and then quickly get into some of the meat of the talk. And feel free to ask questions during it. So I'd like to start acknowledging some of my short and long-term collaborators on this project. You know, they're listed here. Some of them are mentors, others are actually students and postdocs, and also the support of many agencies, including DOE, ASCR, FES, LDRD programs at Oak Ridge and Los Alamos, the Los Alamos Thermonuclear Pair Initiative program. Before I begin, just in case some of you are not aware, NIF almost ignited about 10 days ago. It's a really exciting piece of news with laser input of 1.9 megajoules, neutron yield of a few 10 to the 17, 3 times 10 to the 17 is thought to be the ignition threshold. Energy absorbed by the capsule was 250 kilojoules and the fusion was 1.3 megajoules, so 5 times the energy absorbed. Very close, very big deal. And it was not expected. This is the irony of the thing. So, you know, simulations remain critical to predict these systems. This is a brief agenda. I'll introduce generally fusion plasmas and confinement approaches and then go into challenges to simulate these systems and go in depth into 2 distinct approaches, blast of Maxwell particle in cell and applications to magnetic fusion, and also blast of Fokker-Planck and applications to inertial confinement fusion, and then I'll summarize. So just so we're on the same page, thermonuclear fusion is the process where upon reaching sufficiently high temperatures and densities, lighter nuclei combine to form heavier ones and release energy in the process. And fusion really drives birth, life, and death of stars and therefore life on Earth. In stars, confinement is provided by gravity and it works really well in the laboratory. However, this is a very different thing. So what it takes to generate fusion in the laboratory is 100 million degrees. And that's enough. That's because we need to provide enough kinetic energy to overcome the electrostatic repulsion of equally charged particles, in this case, the ions, deuterium and tritium, most likely. In order to reach those temperatures, we need to basically heat matter enough to form a plasma, and that's where electrons and ions disassociate and they become independent and they can move independently. And this is the 4th state of matter, is the most common. And because it's so hot, plasma will melt any surface, so you need to confine it somehow. And there's 2 main approaches considered today. One is magnetic confinement, which relies on a magnetic field to confine this soup of charged particles. And the property that it relies on is the fact that when you put a magnetic field in a plasma, the particles gyrate. around the magnetic field with a certain gyro radius and gyro frequency, depending on its mass and thermal velocity. And what people do is they take a linear configuration, which would have n losses, and bend it into a torus, which is shown here, and that leads to toroidal confinement geometries or devices such as the tokamak or the stellarator. Alternatively, you can compress it, and that leads to inertial confinement fusion. And you can see the tiny capsule right here. It's about 1 millimeter in diameter, and you illuminate that directly with lasers or indirectly with lasers illuminating a whole round, which is here on the right, and then that creates an radiation to bathe the capsule. And upon the radiation impinging on the capsule, what happens is the outer layer called the ablator evaporates right away, and the mass going outward creates a rocket effect going inward, and that leads to hopefully sufficiently high temperatures and densities to actually ignite. So if you look at where fusion plasmas in the laboratory lie in this density temperature plot, they lie right on top right, which means they're the hottest and the densest. You need to go to the solar core to get more dense, and this is actually hotter. They are hotter than the sun. So this is why it's so hard to achieve. So simulating thermonuclear fusion is in fact a very challenging endeavor. The first thing to comment is that simulations are critical because they're virtual experiments. These fusion experiments are not cheap, and they're very big, and you don't really have a lot of chance to iterate. And because a successful fusion reactor confines extremely hot matter at sufficiently high density for sufficiently long, there's not much room for error. And therefore, we need these virtual experiments to guide construction, operation, optimization, and those are simulations. But plasma confinement, or lack thereof, results from a careful interplay of physical phenomena spanning many orders of magnitude in time and space, and that makes it really hard. So what's the first principles model? That's the so-called Vlasov-Fokker-Planck-Maxwell system. Assuming a fully ionized plasma, you have ions and electrons coupled by electromagnetic fields. And that, this already has some significant approximations in it, but it's considered first principles. It leads to the so-called Vlasov-Fokker-Planck equation, where you have, the Vlasov collisionless component, and then you have a collisional term that can actually be quite complicated. And it's modeled for charged particles with the Fokker-Planck Landau operator. This needs to be coupled with Maxwell's equations, which governs the evolution of electromagnetic fields, and those require as input charge densities and current densities. And those in turn can be found from integrals, moment integrals of the distribution function that the Vlasov-Fokker-Planck equation solves for. So these distribution functions need to be positive. They need to be strictly conservative because the original equation satisfies that. They need to increase or keep entropy constant depending on whether you're reaching equilibrium or at equilibrium. And they have really very rich asymptotics. You can impose a number of theoretical limits here that actually allows you to simplify systematically the system, all the way from this description here to resistive MHD and ideal MHD. So the challenge comes from the strong scale separation, and here are a couple of pictures that exemplify that. The one on the left exemplifies time separation, and the one on the right exemplifies scale separation. And this is for magnetic fusion, but similarly, you could generate these for inertial fusion as well. And you see, the fastest time scales in a tokamak. Let's say you have electron gyro motion scales, ion gyro motion, and then you get Phoenix scales, and then you get all sorts of scales in between that govern MHD evolution, but also turbulence, and eventually diffusion, all the way to many hours, as you would like a reactor to operate on. And on the right, you see similarly separation of orders of magnitude in special scales, all the way from electron gyro radii, Debye lengths, to skin depths, and eventually system sizes. So this is a very hard system to solve. However, algorithms can make a significant dent. This is already a fairly old figure from 2003, the scales report. But it's very illustrative of the point that I really want to convey, which is if you actually think cleverly about the systems you need to solve, you actually can make significant progress, much more so than just relying on the hardware improvements alone. And now that we're in the exascale era, we need to be constantly mindful of the fact that algorithms actually break if you start putting them at those kinds of scales, because they cannot scale up. And then you need to think even harder. And here there are two curves. The red is for gyrokinetics. We'll go a little bit into that later on. And the green is for MHD. And here's estimates of the equivalent speed up you got just because you improved your algorithms. And it clearly overpasses whatever you got from the hardware in 2003. The story, however, still remains the same, and I'll show that later on too. So what are the challenges? Well, high dimensionality. We have 3 dimensions in physical space, 3 dimensions in velocity space in principle plus time, nonlinear, extremely multiscale systems. Again, illustrating the scale separation here. And the point is, what we want is to extend the applicability of some of these methods to engineering scales in time and space. And for that, you really require a lot of thought and work into algorithms that actually have, implicitness in time, adaptivity in space, but also strict conservation property, because that's what connects the hierarchy of models and also what ensures that your multiscale solution is in fact not drifting. So what's the, and I'm going to take a very particular point of view here, which is the one that has been driving my research, and you can find others. But I unapologetically will follow, the ideas that I think are most interesting to me here. And that's the use of fluid moment-based models to accelerate kinetic simulations. This actually originated in radiation transport in the 60s, late 60s, by Goldin, his Soviet mathematician. But then later was explored for plasmas by Brackville and Mason at Los Alamos using the so-called implicit moment method, which at that time was linear. Now, actually, that method has been adapted and demonstrated nonlinearly in both magnetic fusion and ICF. And the key idea is that the moment-based systems, those are the ones you obtain by taking moments of the Vlasov-Fokker-Planck equation, can actually be used very effectively to accelerate an otherwise kinetic simulation. So we'll present the impact of these kinds of algorithms in 2 applications. One is Lagrangian particle-based, so-called particle in cell, and that I'll show applications for MFE, and those are actually now, as I speak, becoming mature. And then Eulerian kinetic schemes, solving directly the Vlasov-Fokker-Planck equation on a mesh, and the applications that's had on ICF. Okay, and you'll see that both of them will leverage this concept of moment acceleration. And we'll emphasize as well the importance of strict conservation properties to preserve the fidelity of the solution. So let me begin with the particle in cell one and applications to MFE. And here I'm going to start fairly slow and then kind of summarize progress all the way to MFE applications. So we start with the collisionless Vlasov equation for now. The collision operator has been neglected. And again, we couple with Maxwell's equations. Just noting that this is a singular limit of the Vlasov-Fokker-Planck equation that admits an infinite number of invariants. The ones we're going to focus on is mass, momentum, and energy, because those are the ones that survive collisions at some point. So the particle in cell method basically employs the method of characteristics to solve for distribution function given an initial condition to find it at time f. And that's the formal solution is written right here. And you can see that, these two are the characteristic equations, and it's a nonlinear equation because, of course, the velocity and the force depend nonlinearly on the electromagnetic fields and so on. But what PIC does is it solves this using microparticles that follow these orbits. And then you embed those on a mesh so that you're able to gather moments from those particles. And that's what's exemplified here in this figure. You have the particles moving through the continuum, basically, and the mesh where the fields are defined. And you evolve those particles according to Newton's equation or the relativistic extensions of those. And then you gather moments according to interpolation prescriptions that give you the density and the charge density and the current density, to drive Maxwell's equations. The classical particle and cell algorithm is explicit, which is not multiscale and is not conservative, but it's been really successful and very useful. And it's very simple. Basically, what you do is you stagger positions and velocities updates, and then whenever the position is updated, you gather moments, and then you solve for the electromagnetic fields, and then you proceed in time. Very straightforward to implement, but it's limited in performance because it has CFL or time step based instabilities that require a minimum temporal resolution, and it also has, this is less intuitive, instabilities related to a lack of spatial resolution, and in particular that the pi length is not resolved. And if you recall, that's the smallest one, one of the smallest length scales in your system, then you can actually become unstable. And the lack of conservation properties actually leads to significant drift long-term of the solution, and is not really able to get to some of the engineering skills that we care about. Implicit time stepping may help with all of this. And by implicit here, I mean that now fields and particles are coupled non-linearly in a given time step instead of this time marching procedure that's described here. And in fact, people realized this early. And the exploration of implicit particle in cell started in the 80s with two variants, the implicit moment method and the direct implicit method. And I have references over there, some of them. But by necessity at the time, they had to be linearized and semi-implicit. So that means there was an approximation in the way that these systems were formulated, so such that they avoided the nonlinear coupling between particles and fields. And that actually led to inconsistencies that made the method unusable. What we're going to be pursuing, and what we started pursuing in 2010, was in fact to couple these nonlinearly and enforce convergence between particles and fields. And in doing so, we actually enabled very accurate simulations. And also we can accelerate the convergence using these moment-based methods. So let me start with electrostatic peak as a way to introduce concepts, and then you'll see how these generalize. So let me start with full implicit particle in cell for 1D electrostatic particle in cell. It's a very simple system written on top. You see the Vlasov equation discretized in time, but not in space or phase space. And just taking into account the fact that we have an electric field coming from a potential. And red indicates the implicit coupling between the distribution, between different terms of the Vlasov equation, and blue indicates the coupling with the electrostatic potential. And you can see that there is a moment integral involved. In principle, this F is sampled by particles, as I described before, and there's MP particles. And if you have D dimensions, you have 2 times D number of equations. And of course, you need the field described on the number of spatial mesh points. So you end up getting, if you just try to put this on a modern nonlinear iterative solver, you're going to have unknowns for the fields, but also unknowns for the particles. And the dimension runs away from you very quickly. And it becomes impractical. But there is an alternative, and that's to realize that the particle unknowns are in fact functionals of the potential. And the process is simple, it's the orbit integral. So you can, in principle, formulate a process that does not require the particles to be unknowns. You can actually enslave those particles to the field because they're functions of the field only. And that process, which is formally expressed here, takes you from a high dimensional residual to a very low dimensional one where you only care about the fields, and the particles are just, used as auxiliary quantities, really. And now all of a sudden you go from a really high dimensional set of vectors to a set of vectors that actually only scale as the spatial dimensionality and number of unknowns there. So now you can in fact implement this on a computer as efficiently as you can any other 3-dimensional system. You still have the particles to solve for, but they're not explicitly there. And that's the first element that allowed us to start looking at this. Now you still have to solve this system. You have a residual that depends on some set of unknowns, in this case, just the field. And then what we use is the Jacobian free Newton-Krylov technique to linearize the system and converge on it. And the reason why this is important, this Jacobian free aspect, is because these methods don't require you to actually form the Jacobian to converge in a Newton iteration. That you can estimate the Jacobian by applying finite difference matrix vector products, which is exemplified right here. This is called the Gateau derivative. And if you know F, which we do because that's what we're trying to converge to 0, then you can readily evaluate this quotient here to find out what the product of the Jacobian times a vector is, which is all you need for Krylov methods. And then because the particles are part of this residual evaluation, that Jacobian would be impossible really to formulate, and store. But because we can do this in this Jacobian free fashion and the particles really are just hidden, in fact, this enables the iteration to proceed. The second thing that's important is you get this ability to precondition the system, where this Jacobian system can be, in fact, be affected by an operator and its inverse. And if that operator is close enough to the Jacobian inverse, then you get, basically, you can transform this into something that approximates the identity and converges very quickly. And those two things will be important because in the preconditioner stage, we will use a fluid method. So this is the exact discretization of the electrostatic system written in terms of Ampere's equation instead of Poisson's equation, but they're equivalent in the continuum. And here I'm highlighting all the couplings. But the real important thing is that, in fact, you take this system and you multiply by the average velocity, you sum over all velocities, and you get a strict, my apologies, you get a strict conservation law for energy. That's exact. Because its simplicity has no time-stepping instabilities. It's actually quite robust against aliasing instabilities. I'm not going to show anything about that, but we have work that actually describes exactly how robust. And then we converge on the system nonlinearly, and we'll get energy conservation for free. But that's not the whole story. You also really need charge conservation, particularly in Vlasov, Maxwell. Charge conservation is a really important constraint. And we need to recover. It turns out that if you're not careful, you lose it. The strategy we found, and we've iterated on this since in ways that makes it even more efficient, but I'm going to stick to this explanation here. The strategy we found at the time was to actually subcycle particles such that every time they cross the cell in their orbit integration, they would stop and they would deposit the current locally there. And if you do that carefully, it turns out you can recover an exact charge conservation theorem per particle. So it's a very powerful constraint. Now, if you subcycle and you're not careful, you lose your energy conservation theorem, but you can recover it by doing orbit averaging. And these are ideas that have been around in the magnetic fusion community for a while, since people started looking into these methods. Earlier on, we just adapted them for our purposes. From this slide, the most important thing is that if you define your current in this orbit average sense, that is, you average the contribution along the orbit, and you do that carefully, you recover your energy conservation theorem. And this is an example of what the method can do. And there's a lot of data here, a lot of plots. All the approaches I'm talking about are energy conserving, but some of them are charge conserving and some of them are not. And the ones that are not charge conserving lose this signal. This is, in fact, for an ion acoustic standing wave. This is, for this electrostatic system, a multiscale problem, probably the hardest you can do. The standing wave is one, the shock is the other, and that's really the hardest one you can do here in 1D. And what you can see is the red one. That's the one that uses all the bells and whistles that I described, and it's considered truth. It agrees really well with explicit. In fact, it improves from the explicit solution. All the others introduce some approximation that somehow break charge conservation and don't quite subcycle the particles, right? And you see the solution is far lower quality or even completely lost. So all these improvements to the algorithm are important. This is an example of the shock wave, and we're showing the good solution here. This is for the electric field. I'll show, in fact, what other quantities look like in a second. And we were looking at the impact of linearizing this coupling between particles and fields like this, the implicit moment methods do. And what you get is this kind of an answer here where you basically lose the signal completely. So the linearization of the system has dire consequences for accuracy. And this is an actual plot of the of a shock, completely developed in time, including some of the oscillations behind the shock, which are physical. They're non-numerical. And the remarkable thing about this simulation here is I'm showing three. I'm showing the explicit with its CFL. I'm showing the implicit with a time step of 1 and the implicit with a time step of 10, which is about 100 times larger. And you cannot tell them apart. They really are extremely on top of one another. So this so far I've explained how you would formulate this system, but how would you accelerate it is the next question, right? And very quickly, if you do a back of the envelope estimate of how much you can gain with an implicit method versus an explicit one, you realize that it scales as the length of the system divided by the Debye length, which we know can be a very large number, and that's exponentiated to the number of dimensions. But then, of course, it's gonna depend on the number of iterations that you need to take. The more iterations you need to take per time step, the worse your speed up will become. So preconditioning comes in here to minimize the number of iterations. And what we did is we postulated a fluid model for this system, just because we know what the continuum moment process takes us to, and then decided to use that as our preconditioner by linearizing it, because we're solving a linear system. And the yellow boxes here are input that we can find either from the nonlinear residual itself, or the electric field, or moments from the particles like here. And then the output is the electric field update, which is what we need in order for our Newton's method to converge. And in fact, that worked really well. And we were able to predict exactly the sort of scaling that we got here as a back of the envelope estimate. We've extended this to multi-dimensions and electromagnetic. So it's not just electrostatic that you can do this with. In fact, you can do this for electromagnetic. And here I'm showing some of the convergence results with and without preconditioning for, if I recall, a Weibel instability. And here is without, this is actually a, let's see. This is actually a scaling study with respect to the mass ratio. And the smaller the mass of the electrons, the harder the problem becomes. And you can see that, in fact, without preconditioning, we can clearly tell that the number of linear iterations and the number of nonlinear iterations are both growing. But our preconditioned solution actually barely budges. When I say here's 0, that means my precondition is so good that it doesn't even have to go into the Krylov method. It just comes out and says, I'm done. Similarly, with a grid convergence study in the table on the bottom, you see that there's significant dependence on the mesh size with the mesh size of the performance of the method, whereas our preconditioner eliminates that from our results. And we've also extended this, and this is the application to MFE, to tokamaks, now using the gyrokinetic model. The gyrokinetic model, for those that are not aware of it, is in fact a really successful approximation to the Vlasov-Fokker-Planck equation that's used in tokamaks to study microturbulence, which has huge impact on particle and energy confinement in tokamaks. Gyrokinetics enforces quasi-neutrality and exploits that the gyro frequency of particles are very fast with large guide fields, and therefore the gyro phase angle is ignorable. And gyrokinetic peak suffers from some accuracy issues. It's semi-implicit, and that has what's so-called the cancellation problem. And I'll describe that a little bit in a second. And also it features numerical instabilities like finite grid instabilities, and also some time-stepping ones related to the so-called omega H mode. This is just a simple explanation of what gyrokinetics does and what the basis is. It basically takes the true motion of a particle, which is mostly gyrating and then drifting, to something that approximates the motion by the guiding center, and the gyration is now basically taken as a ring, a charge ring. And if you follow that process in the equations, you end up getting a set of modified equations that have really good properties. And here in this schematic here, you can tell, that gyrokinetic model has significantly shrunk the time scales that supports and the length scales, and therefore makes the simulations a lot more tractable. And if you were just attacking the problem with Vlasov-Fokker-Planck. So we've actually applied all these ideas to gyrokinetic electromagnetic. We're in fact doing so as I speak, but we already have results that are worthwhile reporting. As I mentioned, gyrokinetic peak is semi-implicit and has two numerical problems: cancellation errors, which actually arise from the fact that you need to represent some currents both on the mesh and on the particles, and they don't quite cancel. And that leads to significant errors. And the other one is finite grid instabilities, which actually arise from particles. And these finite grid instabilities actually are a subject of discussion. And we recently had a paper that actually it's now submitted, where we really extricate the issue and show that they're there and how to avoid them. Implicit methods can help with both. And in fact, we've been able to develop an effective fluid precondition, moment-based preconditioner for the gyrokinetic set of equations. And I'm showing here two tables that show dependence with respect to beta and also time step of the number of iterations basically that we get. And you can see that they're largely insensitive to those parameters. And also this is time step normalized to some thermal speed and time step normalized to an Alfvén speed, which depends on the magnetic field. And you can see that, they're largely insensitive to both beta and delta T in both measures. And that's a really good property to have. We've also demonstrated that in fact we can get rid of these finite grid instabilities, and this shows an Alfvén wave with a standard formulation and ours, and you can see that we can propagate that Alfvén wave very cleanly. Okay. We've also verified against other gyrokinetic codes and found really good agreement. So beyond gyrokinetics, what's next? Yes,
Luis, this is Paul. Would it be okay to take some questions if there are any?
Yeah.
With you, I'm looking for a natural stopping point. I mean, I don't see any questions right now in the Discord chat. Okay, so does anybody have any? Okay, so a few people have some questions.
All right.
Thank you. Kevin Royal, JC Maxwell, 3 people are typing, so we should get their questions in a minute, Luis. Sorry. Yes, I've never used Discord myself, but it seems like it works pretty well.
Me neither, actually. It's my, I just took myself out of the presentation, I guess.
Oh, whoops. Sorry about that. So Kevin Royal says, so this is a finite element method approach to theoretical fusion physics?
Both finite element and finite difference, in fact, are represented here. The XGC code, the gyrokinetic code results that I showed are on a finite element discretization, but a lot of the particle in cell results that I showed earlier are finite difference. And a lot of the acceleration ideas are sort of discretization agnostic. You can, in fact, use moment methods to accelerate kinetics in both finite elements and finite differences. Because the key is to lift the formulation up by taking moments, and that's kind of largely discretization agnostic.
Okay, and there's another question: can particle collisions be captured in a standard MCC or DSMC way using an implicit pick approach, or how do you account for collisions?
Oh, that's a really good question. There's recent work on this by at least a couple of groups that I'm aware of, where in fact they've done exactly this. And the one that that comes to mind, which is submitted work, they've actually showed that if you do MCC with an implicit energy conserving method, you actually get the right thermodynamic asymptotics with collisions versus doing it with explicit methods where the energy, even though the MCC itself, the Monte Carlo collisions, are conservative, the Vlasov piece isn't, as I just explained, and that can lead to a lot of drifting and secular growth. So in fact, you can, and people are doing it, and you get significant benefits from using an implicit method that's energy conserving.
Okay, there's one more question. Well, is momentum conserved in these codes?
Oh, very good question too. So some of them are, or in some limit, you can conserve momentum. It's a brittle conservation property. As far as I know, the electromagnetic ones don't. The electrostatic ones, some of them do. Right now in PIC, we don't know how to conserve both energy and momentum. You have to choose one or the other. The one that we found to be robust and beneficial long term or more beneficial long term is energy conservation. And we have specific measures of how our momentum conservation breaks and how bad it gets. And in practice, it doesn't get to be that bad. And the reason is that the orbit integration, which is subcycled and is careful, it can actually detect, sharp turning points and that sort of thing. Actually does quite a good job of limiting the impact of not having a strict momentum conservation. But we do not know how to do both at the same time right now in PIC.
Okay. So I don't see any more questions. So why don't you go on?
Those are good questions. Those are good. And I don't, interrupt me whenever.
Okay.
No problem. So beyond gyrokinetics, gyrokinetic makes this assumption that you have a ring of charge, and that can be problematic at boundaries, also weak magnetization regions, or when you have strong gradients that are comparable to the gyro radii. So, you'd like to actually be able to limit to the gyrokinetic model when appropriate, but then stand back from it also when appropriate. And we're actually looking at numerical solutions that are able to do this and transition seamlessly between drift kinetic, gyrokinetic, and full orbit. And these are early results from a particle orbit integrator that's in fact able to do just this. You can show that it can take the full orbit limit if the time step becomes small enough in some measure, and asymptote to the gyrokinetic solution. I mean, this is a single test particle orbit, so we're not coupling with peak yet here. But it asymptotes to the right asymptotic orbit, the gyrokinetic orbit, or the orbit that a gyrokinetic particle would follow when you take the time step to be large with respect to the gyro frequency. So these are ideas that hopefully will propagate into in future codes, and will be able to allow us to simulate some of these regions which are not properly in the regime where gyrokinetics is valid. So now I'm going to switch topics from MFE to ICF and Vlasov-Fokker-Planck. So if there are any remaining questions about particle in cell and MFE, this is the time.
So we can just give a second here. Just a minute. Yeah, I don't see anybody typing.
Okay.
So go ahead.
Right. Okay. So as I explained earlier, you're trying to compress a very small spherical capsule through this illumination ablation compression process. And then in doing so, at each radial position, you may get a distributional function that may or may not be a Maxwellian. And it obeys this Vlasov-Fokker-Planck equation. And the acceleration is given by the electromagnetic fields. And collisions are important here because they can take something that's clearly not Maxwellian and drive it to a Maxwellian with enough time. Kinetic effects actually are important in certain ICF implosions, and this is experimental evidence to that effect from a paper by Rosenberg et al., actually from MIT in 2014, from Petrasso's group. And it shows basically, the bottom here is the Knudsen number, is the ratio between the mean free path and the radius of the shell. And here is on the vertical axis, the deuterium yield, neutron yield over clean, as it's called, which is what a one-dimensional right hydrocode would predict. And you see that as the Knudsen number, which when it's small, you asymptote to the fluid limit. So here, my apologies, here is the fluid regime. Here is the really kinetic regime. And you can see that as you start in the fluid regime, the codes do a reasonably good job of predicting the yield, but as you start moving on to, the more kinetic regimes, you don't. And some of the implosions that people use to diagnose and develop diagnostics are actually in a kinetic regime. So the first principal model is the same, Vlasov-Fokker-Planck equation plus Maxwell's equations, but now we're going to include collisions. Collisions in these systems matter. And these collisional sources actually are advection diffusion equations in velocity space. And the coefficients can be found from solving from a couple of potentials called the Rosenmuth potentials, which are here in orange. And these actually are found from solving a couple of Poisson's equations, which are sourced by the distribution functions themselves. So it's a very nonlinear integral differential system to solve. And then you need to couple this with Maxwell's equations, like I described earlier. So again, exceeding a multiscale system, but also mathematically complex. And what we did to begin is to actually restrict ourselves to one-dimensional geometry, spherically symmetric or planar, depending on what problem we're trying to do, and two velocity dimensions, which is a proper reduction of the three-dimensional space when you only have one-dimensional fields. And we consider asymptotic limits. We actually took an electrostatic approximation, which in 1D spherically symmetric is what you need to do. Quasi-neutrality, so we don't allow charge separation, and bipolarity, so the current has to be 0 in 1D, and multi-D is not true. And then we eliminate, so this way we eliminate a number of fast timescales and small length scales from our system. And we also considered at the time, this was 2015 or so, fluid electrons. Now we actually have kinetic electrons, but I'm not going to talk about that. And that's our model. That's how we started. And ions remain fully kinetic and allow for multiple species. So then the equations would look like the Vlasov-Fokker-Planck equation for ions, or for electrons. You actually have a set of moments, and then you impose quasi-neutrality here and a bipolarity here that gives you electron densities and velocities. And then you have an Ohm's law to find the electric field. Well, if you try to solve this system using a uniform mesh in phase space and explicit time stepping scheme, you never get there. You will never get there. You can estimate the mesh requirements, and they are in the 10 to the 12, 10 to the 13 unknowns, even in 1D, 2D, and that's because of the separation in velocity space when, you know, from when matter is cold to when matter is hot. Also for different species mass, like electrons and ions, which is already very disparate, but you can have also higher, you know, heavier ionic species. So that separation leads to this kind of requirement. And also time step requirements because of the collisions, numerical timescales related to collisions. And you find that you need 10 to the 10 time steps to actually cover the, you know, between 1 and 10 nanoseconds that an implosion lasts. So completely beyond our resources right now. So you need to innovate algorithmically. And again, you know, we consider implicit methods, and I'll show a little bit schematically how we do this. Also, we actually invested a lot of time being careful with our formulation in phase space, and we actually adapted our mesh in two ways. We actually move the velocity mesh according to the bulk velocity and the thermal velocity of the particle, and we do that in space and time, so that we shift our mesh as we need to resolve optimally the distributions functions that develop. And in space, since these capsules are imploding, we also follow those boundaries and actually move the radial mesh along. And we do this while being fully conservative. This is critical. I'll show an example in a second, an example. So these strategies actually have saved us 12 orders of magnitude in computational complexity versus brute force. And this is not an overstatement. I'll show what we can do. So again, the phase space grid adaptivity shifts and scales the mesh according to the solution, and we also scale the spatial mesh according to the motion of the boundary and also the solution. And we actually implement all this analytically in our equation. So this is what our equation looks like after we're done with the transformations. And we impose conservation properties on this equation directly. These properties are mass, momentum, and energy. And in principle, Gauss wave, we're solving for kinetic electrons. And if you don't solve for this, if you don't enforce these constraints, you actually get the wrong answer. And we, in fact, what we did is we took our equations and enforced some nonlinear constraints in our discretization that would take care of these. And each of these boxes is one of those constraints that has a very specific definition, such that when you do the moment integrals, everything cancels out. With all these tricks, you actually can get to something manageable. Now, all of a sudden, because of the adaptivity in phase space, the number of mesh points in phase space is 10 to the 6, 10 to the 7 versus 10 to the 12. And the number of time steps is order 1,000 or 10,000 instead of 10 to the 10. So now we can do the simulations, in fact, with machines that are available now. This is one example of a relaxation problem that exemplifies the mesh savings that we can get because of this phase-space adaptivity. In this particular problem, we saved factor of 1 million over what would be required in terms of resolution if we had a uniform mesh. And this is an example of why conservation is critical. In this case, it's just a temperature relaxation problem between electrons and protons, and same exact mesh, same exact formal order of accuracy, but you get the right solution on the left with conservation, and you get a completely wrong solution on the right without it. So how do we accelerate this system formulated in this way? Well, what we do is in fact take moments like I described earlier, and these moments now are solved along with our original equation. And this is a Picard iteration, so to speak, where we solve for the let's say, moments, and we find electric fields, densities, and energies and all that. And then we feed those quantities into the Vlasov equation, which all of a sudden looks linear because the nonlinearity through the fields has actually been eliminated by the iteration, and then you can solve for that and obtain an updated distribution function that then can get you updated coefficients to solve for the moments. So that's basically what we do, but we do this while not spoiling our conservation properties, and that takes a little bit of care. So the impact of this multiscale moment preconditioners or accelerators is huge. I'm showing here what happens without holo. Holo here is high order, low order. High order is the kinetic solution, low order is the moment solution. And here I show what happens when you start increasing the time step versus the collision frequency. And you see that if it's small enough, it's blue, it converges pretty quickly, but then the moment you make that large enough, it doesn't, it actually completely stalls. Whereas if you use this moment description, you recover essentially the convergence, almost independent of the time step. And that's the property that we're looking for. So let me actually show an application of this solver to an actual exploding pusher capsule in ICF. For this particular set of experiments, right hydro is typically off, in terms of the neutron yields and the temperatures that the experiment predicts and versus what the code tells us. And in this table, you exemplify that. You see the temperature, the diagnosed temperature from the experiment is 13, but right hydro tells us it's 21. And from DT is essentially 20, and from the right hydro code, and the experiment says should be 14. And you get about an order of magnitude yield mismatch between the experiment and the right hydro code. So in this set of experiments, in fact, we expect that we'll have kinetic effects because of the Knudsen number. And we actually show significant savings for these particular simulations of the order of 10 to the 7 for the implicit solver, and 10 to 11 for the number of degrees of freedom. So this is just technicalities of how we drive the solution. I'm not going to get into those. This may be more of interest. This is an actual simulation using this tool. And here I'm actually simulating the deuterium and tritium separately as two separate species, and the glass as a separate species. So we combine the silicon and the oxygen as a single description here. And also I'm putting the right hydro solution on top in dashed blue. That's on the set of top curves here, and you have density on the left, velocity, middle, and temperature on the right. And on the bottom, you can see the distribution functions integrated in the perpendicular velocity. So this is just essentially a long radius for deuterium, tritium, and glass. And you can see right away, you see these wave breaking structures here, and those are purely kinetic phenomena that cannot be captured with right hydro. And let's see if this goes. So this is just about when the spherical implosion is about to converge at the origin. And you can see that, we can find significant separation between deuterium and tritium. We also find significant penetration of the glass into the fuel. And the temperatures also show essentially that, these species are separating and moving. Deuterium is faster than tritium and is moving ahead. And we get very significant kinetic structures happening in the PDF that we're solving for. Okay. So let it finish now, and this thing converges to the center, and then that's where it produces most of its fusion reactions, and then rebounds. This is an actual plot of the experimental yield over the simulated yield for a range of field densities for these exploding pushers. And what you can see here, so solid circles here is right hydro, and open circles is our Vlasov-Planck code. And you can see that for a large range of field densities, we get spot on agreement with the experiments. At some point, we get some disagreement of about a factor of, 2 or 3 or so. And that's because we also have approximations in our model. So at some point, those we're going to break too. but we get otherwise really good agreement. And in fact, there's lots of analysis and results that are coming out of this tool that are now in collaboration with the MI3 group being documented. So again, incredible savings from the algorithms for this particular problem. So what's next in ICF modeling? Well, the real frontier in ICF is hole rounds. That's the cylinder outside for indirect drive that gets illuminated with lasers, and then that laser energy is transformed into radiation, X-ray radiation that bathes the capsule. And it's a critical energy conversion mechanism from laser to X-rays. And this hole room environment is by design rarefied or vacuum. And therefore, kinetic effects are going to be important. It cannot be modeled correctly in red hydro. And in fact, we're taking care of that as we speak. We also may get electromagnetic fields that have been measured in hole rounds and cannot be neglected, not just electrostatic. So uncertainty in this system, in fact, is preventing progress. And we've undertaken a very ambitious project at Los Alamos to, in fact, improve on red hydro for these systems so that we can get better set of virtual experiments that can explain the results that we're getting. And that's it. So this is my last slide. And I hope I convince you that, the modern multiscale algorithms require these multi-fidelity descriptions that are quite effective in accelerating otherwise really stiff simulations. Asymptotic preservation is key so that you get the consistency between the different models in the hierarchy. And asymptotic preservation is also key so that you can actually transition correctly across scales. And we've applied the concept successfully to simulate both magnetic fusion and inertial fusion experiments. All right, I'm done. Thank you.
Thank you, Luis. It was excellent. Thank you very much. Let's see. We have time for questions, right, Christina? We probably have. Okay. So I'm going to go to the Discord window. So I see people are starting to type questions in, Luis. So
yeah, I'll leave the presentation up in case I need to go
that's
back.
a good idea, and I'll just read the question.
Or if anyone on Zoom wants to ask questions, just use the raise hand feature and we can just unmute you.
So could you elaborate more on the challenges in hole rounds in the simulation?
So let me describe one of the key problems that we're having right now. So if you so when you illuminate the laser, the wall of the hole round with lasers, what happens is the plasma blows off and you get these bubbles of plasma that are coming off the walls. And this is a cylindrical device. So they're coming off from, essentially a cylindrical system towards the center. And at some point they're gonna collide. And what happens in that collision is critical, right? If the conditions there tell you that these bubbles should interpenetrate, and they don't, because your model does not allow for that interpenetration or not sufficiently, then what you're gonna get is, instead of interpenetration, you're gonna get this pileup of material and corresponding density increase, right? Now, the laser deposition is critically dependent on the density. The critical density, as it's called, is what determines where the laser is going to be depositing most of its energy. And if you capture that wrong, then you're going to get, but because you get a physical pileup, then you're going to get the laser to actually deposit its energy in the wrong place. And then on and on it goes. So, then of course it's in the wrong place. So then, it starts actually mocking up the symmetry or lack thereof of your radiation source towards the ablator, and then your whole implosion ends up being a mess, right? Just because you could not really predict with high fidelity where the laser was depositing its energy, because the approximation underlying the motion of the plasma was not right. So hopefully that sort of illustrates the problems that we're dealing with.
Okay, so there was a sort of second part to his question, to the question. Also, to step back, what are the initial conditions for the electrostatic ion acoustic shock, and what are the numerical challenges that arise in the shock problem itself?
Oh, for the electrostatic problem, what were the initial conditions?
Yeah. what are the initial conditions for the electrostatic ion acoustic shock?
Well, so you basically, perturb the system with a sinusoidal perturbation, and depending on what you perturb, you get a standing wave or you get a shock that propagates. And in fact, if it's a nonlinear perturbation, then the shock propagates and steepens. That's the physics, right? And the challenges there, really, this system is not that hard. Explicit can do it just fine because it's a 1D, 1V, and it's multiscale in the sense that the time scale for the shock steepening has to do with ionic time scales, whereas electrons are the ones that are stiff. And if you use real mass ratios, then it becomes a problem that can be stiff. But it's not a hard problem to simulate. The problem is that implicit methods could not do it before, right? Even this problem that's in 1D, 1V, they would basically fail, and they would give you really bad answers. So it's where you need to begin. So the problem itself is not the hardest you can do. It's much harder when you go electromagnetic. There you really start challenging the solvers. But if you cannot do those simple problems, nobody's going to believe you can do the hard ones.
Right. And now I think we're having another question. Someone's typing in the window, JC Maxwell. Thanks. They said thank you. So any other questions? So another question. Two questions. Is there a hybrid version of this implicit Vlasov plus fluid solver in the works? So is there a hybrid version of this implicit?
There is. I have not brought it up because I have an hour. But yeah, we've actually generalized the particle in cell. So the Vlasov-Fokker-Planck work that I described here is hybrid. Okay, in the sense that electrons are a fluid and the ions are kinetic. We've since generalized that, but I haven't really discussed this here. On the particle side, we have in fact published a hybrid fluid electron kinetic ion formulation using particles and being able to conserve properties. And in that context, in fact, we know how to make both energy and momentum to be conserved. So once you kind of go from the full particle and you allow one of the species to be a fluid, then you actually can enforce both. So yes, there's work out there. You can find it under my name in JCP. I think it's 2018. But that's, and we're now, that was Cartesian. We're now generalizing it to use, curvilinear geometry so that we can actually attack some realistic problems. Thank you for the question. Yeah.
Okay. There's other questions. I don't see it. Maybe I could take it as more. Oh, here. Okay, so there's another question now. One more question they're saying. So they're typing this. And Christina Rayer is typing also. So what MFEs can you simulate with this or are planning to with this hybrid solver? I guess.
Okay, so actually, in principle, you could simulate tokamak disruptions with it, right?
Ah, okay.
It's a perfect system for that because it's a very dynamic system where electrons really at that point are just focusing on keeping the electromagnetics in check, and the ions are the one that are controlling the whole motion, right? And this is one of our interests. One of the examples that I have in a paper that the curvilinear paper that I mentioned is in fact in helical geometry, and I'm starting to get at some of the MFE type problems that we're interested in. So if you're trying to simulate, systems that are quiescent, well confined, then you really should use gyrokinetics, extended perhaps to do electromagnetics, which is what we're working on, as I mentioned, because those are much better suited to, to capture the small, the careful interplay between electrons and ions, in a kinetic regime, right? So hopefully that answers the question.
thanks. Let me see if there's any more questions. I could end with a short question myself. So I think you showed in your talk that fluid solutions can be effective preconditioners. Is that what you said?
Yeah,
Yeah.
or accelerators. Yeah, you can look at them both ways. Yes.
Okay, so in electromagnetics, wave equation, coming up with preconditioners is notoriously difficult. Do you have any thoughts on that?
No. No, I haven't thought about that problem. I know you guys have been interested in that for a while.
Right.
But it's a worthwhile problem to think about. I just haven't had the chance to, to put myself knee deep into that problem. So we should talk a bit more to see if there is room for, for a future, interaction on that.
Yeah.
Because I haven't thought about it, and I think the problem is really quite particular, and you need to think through some of those nuances in order to come up with something that actually helps.
Okay. We just check the chat window to see, I mean, the Discord window to see if there's, I think that's it. Okay.
Okay. All right.
Thank you very much, Luis. It's been very
Thank you
interesting.
much for the opportunity. I really appreciate it. Keep in touch. Okay.
Yep. You too.
Thank you. Thank you so much.
You bet. Thank you, Christina. Bye.